All right, everyone. In this video, we will discuss Markovnikov versus anti-Markovnikov. These are regioselective terms. Now, I'm going to start by prefacing by saying that in the textbook, they might say that the Markovnikov carbon is the more substituted carbon of the pi bond, and the anti-Markovnikov carbon is the less substituted carbon of the pi bond. That's how the textbook usually defines it and how your professor might have defined it. I'm going to offer an alternative way of thinking about this that I think is ultimately more accurate to all cases. Let's define the Markovnikov position of the alkene pi bond as the carbon between the two that would stabilize a positive charge better. It's not necessarily the most substituted always, but it would always be the carbocation position where it's more stably accommodated. And the anti-Markovnikov carbon will be the carbon that stabilizes the positive charge more poorly. So follow me on this. When we react the alkene pi bond with a proton electrophile, specifically a proton electrophile from a strong acid, all the pi density could be utilized by this carbon to bond to the hydrogen, leaving the other carbon that was part of the pi bond positive and deficient. Alternatively, all the pi density could be utilized by this carbon to bond to the hydrogen, leaving this carbon deficient. If those carbocations differ in stability, one of them will be preferred to form over the other, and the one that is formed preferentially is the one that's more stable. Here, the more stable carbocation is the tertiary alkyl compared to the secondary alkyl. Because they're both alkyl cations, the tertiary is more stable than the secondary as a function of hyperconjugation. Therefore, we'll say that the Markovnikov position is the tertiary position, and the anti-Markovnikov carbon is the secondary position. So to repeat that, here we have our Markovnikov and our anti-Markovnikov. The Markovnikov position is the one between the two that stabilizes the positive charge better. Looking at the next example, I'm going to electrophilically add my proton. I'm considering the formation of a secondary benzylic carbocation versus a secondary alkyl. The more stable carbocation is the secondary benzylic carbocation. That's because this carbocation position is stabilized via resonance. It's delocalizable, whereas the secondary alkyl carbocation is not stabilized via resonance. Therefore, the secondary benzylic is the Markovnikov carbon, secondary alkyl is the anti-Markovnikov carbon. So we have Markovnikov and anti-Markovnikov. Looking at the next example, we will electrophilically add our proton, consider each carbon balancing a positive charge. We have secondary benzylic versus tertiary alkyl. The more stable carbocation is the secondary benzylic carbocation. That will be the Markovnikov, and the tertiary alkyl is the anti-Markovnikov. In a former video, we discussed carbocation stability, and when we did so, we said that tertiary alkyl was approximately the same stability as a primary benzylic carbocation. Now, what that means is that secondary benzylic is more stabilized. So here, the Markovnikov carbon is the less substituted position, but nevertheless, it's overall more stabilized. This is why I prefer to think about Markovnikov's rule, not just about the primary, secondary, tertiary aspect, but holistically about the stability of the carbocation. In the next example, we will electrophilically add our proton. Two possible carbocations are tertiary benzylic versus tertiary alkyl. Tertiary benzylic is more stable. That will be the Markovnikov. And the anti-Markovnikov will be the tertiary alkyl position. All right. Now, this next example illustrates the effect of lone pair atoms. So imagine we electrophilically add the proton, creating a carbocation. The positive charge forms here. That's tertiary, but notice the positive charge isn't directly bonded to the oxygen atom. Therefore, the oxygen takes on an inductive withdrawing effect, and that destabilizes the carbocation. So really, that's a subpart tertiary stability. In the right structure, the carbocation is directly bonded to the oxygen atom, and therefore the oxygen can resonate with the carbocation, stabilizing the positive charge via a full octet resonance structure. We love that. We go bananas for full octet resonance. So even though this is technically a primary alkyl cation, because there's the full octet resonance, that's ultimately more stabilized than this tertiary alkyl with the withdrawal. So again, we're seeing an example here where the Markovnikov carbon is not the most substituted carbon. But nevertheless, we'd say the Markovnikov position is the one between the two of the alkene pi bond that would stabilize the positive charge more effectively. All right. So this is ultimately really important. We'll discuss regioselectivity in a little bit more depth later relating to comparing two structures and their regioselectivity. For now, this video is essentially getting us acquainted with this idea of Markovnikov versus anti-Markovnikov. And anytime you're doing a reaction of an alkene, you want to kind of annotate for yourself which is the Markovnikov position and which is the anti-Markovnikov carbon, as ultimately certain reactions will be regioselective, favoring either an outcome at the Markovnikov or the anti-Markovnikov position.